Okay, so here we are on page 189. And transformations of variable. Okay, fitting a linear model to non-linear data. So lots of times you don't have linear data. So the first thing that you want to do is see if you could transform the data to make it look more linear. So we have these 4 assumptions that we've been talking about all along, and let's look at them again. So these are these assumptions of linearity. Your data should look linear, so you should plot it first to see if it looks linear. Okay? So let's say we do it. So obviously, the ideal, I'll just look at the positive x and positive y coordinate just to make it a little simpler here. And so your data should look sort of roughly elliptical shape. And we've seen a lot of data that does not look like that. That's kind of the ideal, right? And it obviously follows some kind of linear pattern here, right? So this is the ideal. Sort of this elliptical shaped plot. Now, often you don't see something like that. And actually, the first question on your exam there were a lot of, the one where I showed you 6 plots, and I said, is R appropriate to use? Well, some of them, it wasn't appropriate to use because there was a lot of curvature. For example, you might have something that looks like that. And if you fit linear data to it, it would not detect the relationship. Or, so this is bad. And something like this. I mean, this happens all the time. Like if you just think of anything that's good in moderation, but bad at the extremes. Like sometimes, let's say this was X was some drug, and this is death rate. I mean, a drug that's good for you, not like a street drug or something. So the death rate goes, if you have too little of the drug, you're going to die, right? And if you have too much of it, you might die. You do an overdose, but right here would be perfect. So something like a linear plot wouldn't capture that relationship because it's, and same with something like this. And my favorite data set that looks like this, that always surprises people, is money and happiness. I mean, there's so much data that looks like this because everybody wants more money, right? And they think, oh, I'll be happier. So you do. So this is like dollars would be a good example. And some, not only just all sorts of measure of happiness, like stress levels, everything would be here. So what it says is there's a steep rise when you go from being really poor, to having some money. Of course, it's way better. But as the more and more the money you get, it levels off, and there's no increase in happiness, and sometimes there's a decrease. So this is like, oh yeah, super happy. It's terrible to have no money, right? So it makes it real difference there. So we want to capture these relationships, so this is bad too. Why do we want to capture it with this? When we could describe it better with a curve, we could describe it better with a curve, but if we want to use the models that we've been using, we have to do a transformation so it looks like this. And lots of times that's the best fit you can do, and then you transform back to this. All right? So what does it say here? It says to check the assumptions, you can look at either the scatter plots or the residual plots. What are the residual plots, and why would you even do that? So remember what a residual is. A residual, you make a prediction, and the residual is just a little distance off the prediction. So here's a big error, positive, here's etc. So in all of these plots, the residuals are there. There's a giant residual here, giant residual here. They're all here, so why do a residual plot? You don't have to unless you can't see the pattern very well. I mean, these are very obvious. For example, if we did a residual plot, it would look exactly the same way except we'll do it of any of them we could do it. We could do it of this one just because we have more room. And so what would it look like? What does a residual plot do? So there's two ways to do it. You could put the x's here, just like we have them, and instead of having this be y right here, what you can have are the errors around y, the residuals. So it would have 0 here, because the average of all the residuals is 0. So this is the plot of the errors. It's the errors, the distances from y. So, right? So instead of having a line like this, we're going to have the same pattern, right? So these are the negative errors. They'd be down here, and it would just be easier to read. In this case, it's kind of useless because it's the same thing. But often, it's easier to look at, but often you can hardly detect it unless you do this, because what you can do is you can change the scale around here. And when you change the scale, you can magnify it. So if something looks pretty linear, it's always good to check. If it's obviously violating, you don't need to do it. But let's say it looked really linear, you might not detect small differences around here unless you expand it and do this. That's one example. And that's very much like the homework that I'm going to post. So I'll warn you about this. So this is right here. It's usually easier to spot assumptions by looking at the residual plots, and sometimes you can't. That's the only way you can do it. So in homework, your next homework, which I haven't posted yet, homework 21st problem, that's what it's about, solar system problem. You're going to not be able to it's going to look really linear until you plot the residuals, because then it can change the scale of y. So that's a good example to see where it can be really useful. All right, moving on. We've already talked about all this stuff, but now we're going to dive into it and really solve the problem. What happens? So I want to go through it in your mind again. So the errors in the true underlying regression model must be mutually independent. We talk about that all the time. Independent, equal variances, and normal. IID, independent, identically distributed, normal, with the 0 errors, and little perfect normal curves around. I'll show you pictorially, but we talk about it all the time. So let's draw a picture of it. So independence. Well, can we model randomness is the key to everything we're doing. We want these draws to be, we're modeling variability, random variability. Our null is always, what's due to chance error? That's random variability. That's the null always. And we're trying to detect something else besides that, a signal, right? So if we can't model our data as random draws or the errors as random, then we can't use any statistics. So this is probably the most important. But where it shows up all the time is in these correlated errors, like when on the x variable is time. But we haven't really done that examples because we don't have time to do everything. So you'd have correlated errors all the time when you're looking at data across time. So you have to be very careful here. But basically, you want to model the data as random. So a typical violation would just see any grouping whatsoever, right? It's supposed to be random, right? So the draws, let's just remember our ideal. So let's say we even had an ideal looking one like this. And how would you know that it violated independent draws? Well, you might have these clusters, like groupings. We've seen how groupings often, mess things up, right? When you have two groups, if we're talking about causation, the causality can be messed up. But here, let's look at something like this. Check that the plot and the residual does not show grouping. For example, I'm just going to give you sort of extreme example, let's say you were looking at a group of people, but there were clusters of triplets or something. So triplets. You really don't have 3 independent points on anything because those points are going to be very correlated. Groups that are extremely alike, and you shouldn't count them as independent. It would make it seem like your sample size is much larger than it is. So that's the idea. This is bad. These are all bad, bad. Ideal, just remember the ideal. We'll just draw the ideal all the way down. Okay? All the way down. This is the ideal, so we don't have to redraw it. So I'm just going to show you the bad things. All right, so the variance has to be equal across all the x's. So, for example, variability of the y should be the same. So you want to check the spread around the regression line. It should be the same across the plot. People say this is, the term for it is homoscedasticity, same spread. All right, so something in our data that comes up a lot that you'll see is some kind of fan-shaped data, like that. So the errors are very small around here, but as you get further, it follows a linear path. But around here, they're very clustered, and then the further out you get, the more the errors. So this would be a violation. So we'll look at transformations and things to do in all these cases when we have these violations. And the last one is this normality of the errors. That comes up it's particularly important if you have fairly small sample sizes. And it's a condition. It's one of the assumptions to put error bars using the t-test, right? You have to have normality of the errors. So what does that look like even? How a residual plot really won't help in looking at that. We're going to have to do something else. The errors around the regression line at each value of y are approximately normal. So you have to do a histogram of the errors. That should look approximately normal. So here, what do I mean? So it's very hard to see this in a scatter plot, but the idea is you have the ideal scatter plot. So I should draw the ideal one again. This is the ideal one. You make a, elliptical shaped, right, like that. And that any slice across this, like you take a slice across the x's, inside there, you should have like a normal curve inside here, meaning that more points are clustered here and very few out there. So wherever you go, it should be, I'm sorry, I didn't draw it well, but it should be a normal curve centered there, and then you can use that standard deviation of the errors around it to say that, 1/3 of the points are between, not 1/3, 2/3 of the points are between one standard error in either direction, 68% of the time basically, and 95% of the time your data will be within 2 standard deviations of the errors. That's assuming you have this, okay? And then to make sure you have this, so this is your good plot. And then if you plotted this, you'd have, and this is a plot of the errors. It's it's a histogram. So what is it going to look like? You see, what I'm saying is, let me show you the bad one first so you know the difference. Okay, so a bad one would look something like what? You'd have that same nice curve here. But now, if you go through a slice, you'll have something that doesn't look normal here. Like there might be a hidden binary variable in there that you're not including in your model, something like that. And so you need to include it because look, it could be like, there's no normal curve here. It's like on either end, you'd still get this and maybe a few in the middle. But there's some, because it's not the only thing, but there's some, that does not look normal. It looks sort of the opposite of normal. It's going to be like this or something that's weird. Okay? So that would be an alert that you're missing something that's making your data, you've left something out or you have something messed up. So this is really you can't really see it very well, but if you plot the data, the histogram of these errors, you can see they should cluster around just like a normal curve. Most of them should be around, 0. They should follow sort of like this. And you might think, we violate that all the time because it doesn't really look normal at the edges. You often see things that don't, but that's because there's very few curves out, very few points out there. So you can't really tell. But in the, along where there's a lot of points, it should look like this, okay? And where's this? So this is good, and bad would look like what? I'm doing extreme cases here, but bad would look something like you plot the errors again. So here, these are your histogram of the errors, right? And there's hardly anything around 0, just a tiny bit, right? In fact, it gets all your data is out here and out here. And then you know right away, whoa, this is not good. So this is pretty useful, something like that. That would be really bad. Okay, so let's look at some real data and see what we can do and how we can see how we can make things more normal. So first, let's look at some real typical patterns you'll see and the most typical data transformations you'll do. So this is about transforming nonlinear data into a linear plot by re-expressing the variables. And by far the most common one that comes up is taking logs, doing plots of the logs. So we're going to concentrate on that mostly. So if the scatter plot follows a non-linear pattern, try the following 6 steps to make the plot linear and to make the errors around the regression line normal. Okay? So first thing you want to do, if you see that it's not linear, it looks really screwy, your data, why don't you try transforming? I like to start with the y because there's just one y, and lots of times you're dealing with multiple x's and stuff, so just start with the y. And by the way, these rules are just guidelines. They're not like you can make up whatever rules you want. I'm just thinking this is typically what people do, okay? So if it's symmetrical, so you just want it to be nice, like in symmetrical. So if basically doesn't have to look exactly normal, but you certainly want unimodal and sort of like that. So I'll say roughly normal and not highly skewed to one direction or the other. Roughly normal. Just leave it as it is, okay? Leave the y variable as it is. Something else. Then try the x, okay? And start with the x and see how that is. And usually one or the other is not going to be normal or symmetrical. So, but more often you'll see something like, let's say it's right skewed. This comes up with so much data. We'll look at income data. Anything sort of that's cut off, most things that are like really sharply cut off at 0 and then can go unlimited in the other direction like income. So, right skewed means what? That the bulk of the data is down here, right? The bulk is down here, and then you've got this long, long, long tail where the average is much greater than the median, right? Well, then what you want to do is do a transformation that brings these big values in, right? So what are the transformations that would do that? Well, a square root would, because 100, like let's say you have data from 0 to 100, take the square root of it, it would go all the way down to 10, right? Whereas 25 would go down to 5, 4 would go down to 2, 1 would stay at 1, and the opposite would happen with, would spread these out more, below, the square root of a quarter is a half, so those values would move up. So you'd get more symmetrical data, okay? So which one do you do? The square root, but let's say that didn't work. The log is an even more drastic reduction of the big values. That's even easier to see. Like, let's say you have data up to, I don't know, a billion or something. And then you have, so that's like a billion would go from 0 to a billion. We wouldn't be able to fit the data that's so high if you wanted to keep it, on a regular scale. you wouldn't be able to fit it on the page, obviously. So you'd have to you really want to be able to see it all. So you'd have to, instead of writing if it was log base 10, a billion it's 10 to the ninth. So you would have to, instead of having a billion way out here, it would drag it into 9, right? And a million would be dragged into 6, etc. So it would really drastically reduce it. And so much of nature, so much of our intuition, so much of the way we see the world unconsciously is on a log scale. And you'll see that over and over again. We don't realize we're doing that, but that's what we're thinking on a log scale. So for much biological data in nature and everything, it's wild. It's so common. So we're going to concentrate on this transformation. What does this one do? This one's for sure takes the higher values and makes them lower. 1,000 would be transformed to 1 over 1,000. So the biggest values would become the smallest. So it's the most extreme, but it also, it's less intuitive. It reverses the direction. So it's not ideal. So this is when this log is the one you'll see most of the time. But what if it's the other skewed? What if it looks like this? Well, here, like our exam data, maybe. I'll still make it in the positive. All right, so what if it looks like this? Our exam data always has this tail right here. That's left skewed. And what do we want to do here? We want to do the opposite. Basically, instead of taking a log, we want to exponentiate. We want to take y squared, y cubed, etc., because that is going to spread out these values more. 1 squared is 1, but it will stay there. 2 squared just goes to 4. But 10 squared is going to go all the way to 100. It's the bigger the value is, it's going to spread them out. They're clustered here, so we want to spread this out. If they're clustered here, we want to spread this out. Okay? So, why don't we just take a look at some our own data, and you'll see what I mean. All right. So let's go here. All right, so right here was our fall, this is your data, survey 2. So I'm just looking at, let's look at 2 income. Let's make variables that I asked you. So let's go to the scatter plot. And what was it? It was like, for example, I asked family income. So let's put that on the X, family income. And let's put how much you expect to earn 20 years down the road on the Y. So I want to see the relationship if you're between those 2 variables. Expected income right here. And I can't even see it, right? You just can't even really see it. All this data's clustered there. There's lots and lots of points, but they just look like a clump. That's because it needs to be transformed to a log scale in order to express. Let's see what the statistics are on this. So this was in thousands. So you have to say, how many zeros are there? 1, 2, 3, 4, 5. Okay, so that's really, this is expressed in thousands. That's 8 zeros. So it's gone up to 100 million, right? So that's what this is, 100 million right here. So somebody's family income's 100 million here. And you can see that the average is wildly more than the median. Median is, wow, you guys are rich. That median is 130,000 in our class. Whereas the average in family income, look at this, is 1,352,000. That's shocking. Wow, you guys are rich in this class. So that's the median, the middle person. 130,000. Seems like a lot to me. And the average is 1,352,000 in this class. And they expect to earn a lot more than their family. And so it's interesting. But we can't even see it, right? So what are we going to do? Let's just follow the steps and see how it works, okay? So we're going to go to the histogram. We'll take the Y first, the expected income, and we'll do a histogram and see if it looks normal. It's not going to be normal. We already saw it's very right skewed. The average is much bigger than the median. So the Y was the expected income, and look how skewed it is. It looks like everybody expects to earn 0 because they're indistinguishable because we have to include these big values here. So it doesn't give us any information. It's terrible. So first let's try the first step right here is the square root. So let's try, and that should spread it out. It does, see, but it didn't spread it out enough. So you want to go even more drastic, log. This happens so often. Now we can see the data, okay? So now let's go back to our scatter plot, and now we can take the scatter plot, where scatter plots will do the same thing, but now, and we have family income right here, and we have expected income. So we just did it to the y's. Let's see if that helps. So here I'll just show you. Here was the square root, here's the log. That's the x, sorry. I'm slow. We did it to the y's. So we'll do it this way and this way. That didn't help. We still have a screwy, that does not look linear, right? What happens if you fit a linear regression to it? It just doesn't look right. That's not a linear plot. Okay, and so let's go. So we should try doing the same thing then with the x's. So we'll do the square root, and then we do the log, and look how nice it looks. So much better. And then we can do our regression, and we don't even really need to plot the residuals. You can see that it's pretty good here. Okay? But now we have a linear equation in logs. So that's the idea. That's what we're going to do today. We're going to look at data, and then we're going to see that do transformations, and then how to do our usual estimates, build confidence intervals on data that we've transformed. So that's what we'll do for the rest of the hour. Any questions? But so often you can't even see it unless you do this. So let's go back to the document camera. And all right, so we did this. So we look at the scatter plot with the transformed y and see if it's linear. It was not. If not, try doing the same transformations of the x variable. We did. If the data is straight enough, fit a regression line. We just did. Find the residuals and the predicted values. Oh, I could have. They would have looked good. Now, these right here are to assure the errors are independent with equal variance and normal. All right, so all of these right here, people do them, but you do them, they're all about make a scatter plot of the residuals. We really didn't have to do it because it was so obvious, but you should do it anyway. It's good practice, and it's just as on previous page. All of these are just as on previous page. What do I mean? If you couldn't see it was bad in the scatter plot like this, or you couldn't see it was good, you make, we transform it, and let's say it does look good. But sometimes it's hard for these things to show up. So what you have to do then is to, the residuals are here, is what I'm saying. It's not like mysterious. You make a plot and all of a sudden the residuals appear. They're right here. You have to squint to see them. Okay? So if you can see them, you don't have to do this plot, but everybody does it. Just because it's good practice. But, so you know what to do. Now these, you could make a histogram of those. Okay? And we could do it. We'll do it we're going to go through it with a real data set and really do calculations. So you understand this, and now if they're all met, you can go ahead and make the inferences. All right, so let's go through all that with a data set that I actually ask questions about, and we can do calculations. All right, so below is a scatter plot of brain weight, in grams, on the y, this is the brain weight, and the body weight in kilograms of 34 species of land animals. So 24 of them are mammals, and 10 of them are dinosaurs. So you can't see anything here, right? You really can't see anything. So the first step, is the scatter plot linear? Is it? No, it's just, they're all clustered there. We don't see the 34 animals. And we should go to the data program so you can really see what I mean, but the answer is no. So we are going to go through the transformations. So keep this in mind, but it's so much easier to see if we go to the real data set. So let's do it. So we'll go back to the document, back to the PC, and we have to find that real data set. And this is, you can do this on your own. I just want to show you where this one is. So you'd have to go to Stat 100 here, I think. Okay, so choose a data set, and it's going to be the body and brain weights of the 32 animals. Okay, so let's do that scatter plot that we see. So what we're doing is we're predicting brain weight from body weight. And we should get that same thing that's in your notes. And when we do a regression line, is that the same thing that's in the notes? Yes, 596, a little negative relationship between the bigger your brain, but it's basically a relationship of 0. But this is not good. So we can't even see these. What are these animals? What are they? That's the giraffe, a cow, a human. Wow. Who are these up here that have huge brains for their body? You want to guess? The humans there. Let's see. The Asian elephant. The elephants are extraordinarily smart, yeah. Okay, so that's interesting. But now we can't see what's in here. They're all, and who are these? Whoa, these are all Brachiosaurus. These are other dinosaurs. Tyrannosaurus. Okay, so these are all the dinosaurs. But so what are we going to do? What are we going to do? We're going to go to the histogram. So let's go to the home, and we're going to do a histogram, and first start with the Y, and our Y is brain. So here we are. And again, we can't see it. So we're going to see if we can make it more normal by doing the square root. Better. This is in your notes. So right now, we did the square root. Is it to make it more symmetrical, first try, you'll fill in square root. Right in your notes, we'll fill it in later. But then we'll say, well, next try log. And it's better. Okay, so now we go back. Let's go to our notes and just fill that in. So, look at the histogram of Y. Which of the following best describes it? It's right skewed. Right skewed. So now, to make it more symmetrical, we are going to do these steps, going up this ladder, right? We're first going to try the square root of Y. It's better. And then if that doesn't work, try the log. And when in this program, all the logs are log base E. So they're the natural laws. That's what we're going to be doing all the time. Natural logs. We're not doing log base 10. Although it would work exactly the same way in log base 10. It's just more convenient to use for lots of mathematical stuff to use log base E. So this is log base E. Everything in the data program is log base E. All right, so that's all we did. Now, what if it was left skewed? What would you do? You wouldn't do this. You would go the opposite direction. So you'd first try y squared, then you'd try y cubed, and then you'd do this really drastic one by putting y in the exponent up there. So we'd say e to the y, and that's rarely used. This is a little problematic. You have to have positive data here. We're going to just look at the y squared in this class, but know this. That's e to the y. All right, so let's just turn the page. And this is what we're going to do right now. So we're going to look at the scatter plot with the transformed y and see if it's linear. Okay, that's what we're going to do. And then if not, try the same transformation on X. That's where we're at now. Okay? So let's do that. But first, I just have to go back here, just because it reminds me of something, both with income and with data here, that these little animals down here, we want them to count as much as all the other animals. We want them to, each animal to count equally, and we can't even see these. Same with people who, in our class, who are just average, don't have all that money. I want them to count just as much, and I can't even see them. So this is a sort of way to do that. We're not doing anything phony. We're just making, you want to be able to see all your data, and you want them to count as much. So I say, notice how once you make the scale big enough to see these big animals, and once we make it big enough to see all the super rich people in our class, most of the rest of the data is scrunched near zero. Okay, that's what's happening here. You can hardly see them. And neither can the fitting program. The fitting program, none of us can see them. They're just like a blob, and we're treating them as one point. Okay? And it pays little attention to these small numbers. Yet that's where most of the animals are. That's where most of the people are. So you want a transform that counts the little animals just as much as the big one. And this is one of my favorite children's book called Horton Hears a Who, that says a person's a person no matter how small. So if you know that book, you know what I'm talking about. Nobody could hear the little Who's down in Whoville unless they got all together and shouted. And so it's a very political book that's relevant to our times. And I think just this is an example of how extraordinary skewed our income is. And so when you do all these plots, you want to count everyone and see everyone. All right, I just wanted to do that because math is a beautiful way to display things, to just be able to see everything. Okay, so we're here. So now we go to here. All right, so now what are we going to do? We're going to go back to the scatter plot, and we're going to do our transformations. Okay, so we did this, and now we're going to, and it didn't go far enough, so now we're going to do, we're going to do logs of both of them. And now it looks much, much, much better. I mean, if we look at the residual plot, show errors, I don't know, can you see it more there? You can certainly see there's curvature, but you could see it here too. This is the residual plot. It's just plotting the errors here, and you see how it can change the scale here. It can magnify it so you can really see. It's easier to calculate these differences. That's why people do it. Okay? And so you might be able to see a pattern better. It will expand these out rather than going from -2 to 10 in logs. It's just concentrating around the errors, so you can straighten it out and you can see things better. And we clearly see there's a problem still. Yes, go ahead. I'm so sorry.
So if you change the y's and it still doesn't make it linear, so then you change the x's, you keep the y's changed?
Yes, good question. She said, if you change the y's and the y's look up in the histogram and you get a more normal histogram, don't go back. Keep that log y. Then when you do the scatter plot, if it doesn't look good, then you can change the x's. Log them. Don't go back and change. No. Once you don't want to ever make the histogram of a variable less normal. You want to get rid of that skew. Does that make sense? Okay. So that's the idea. So now, let's get rid of this error plot. We looked at that. That looks okay. Now, what's going on here? You can look at this. It did a perfect prediction for this animal. That's the cat, the kangaroo, and the Tyrannosaurus Rex. But look at how bad it is for some of these others. For the human, for the mouse, So it did great here, but at the ends, it did terrible. For stegos, it just gets bad out here for the elephants. Oh, so it's just good in the middle. There's something wrong with it, but let's analyze it before we figure out what's wrong, okay? So let's go back to the document camera. And, all right, so here we are. And look at the scatter plot. This is what we just did with the transform y and see if it's linear. If not, trying, okay, so it's not linear yet. Now we're supposed to transform x as well and redo the regression log versus log. All right, and we saw after taking the logs of both weights, we get a plot where all the animals show up. We can see them all. We can look at them. The fitting routine also sees all the points about equally, so it comes up with a better linear model. Look what happened. We have much better correlation. Remember, we had a correlation of almost 0 before, slightly negative. Now we see a strong positive correlation between body weight and brain weight. So this is much better. Much better. And the errors are reduced. So this is better. Okay, a better model. This is a good model. The fit isn't great, but it's a good start. Okay, a good start. So now, the one it did a really good job for right here is the cat. And it wasn't so great for the human. All right. Now we're going to look at how we do these predictions on the log transformations. All right? So here's the rounded, just because I didn't want to work with, I thought it would be easier for us to work with. Here's the rounded regression equation. It's the same thing. This right here is linear in logs. You see, it's the linear right now. It has, an intercept plus a slope, and it fits it pretty well. So it's the rounded of what we saw on the previous page. So now we're going to just use this equation to let's find the brain weight of a cat, okay? So first, who weighs this? So we're just going to plug 3.3 kilograms in for the body weight and just solve the equation. Okay, so we'll say, I just plug in there. So it says 3, we're just copying it down, plus 0.32 times the log of, instead of the body weight, we're just going to write 3.3. And so just do that. I did it, and it was 3.82. All right. Now, but the question was the brain weight, not the log of the brain weight. So we want its brain weight. So we just have to anti-log this. Anti-log both sides. So you anti-log this, exponentiate it. I'll just draw this in lightly. So in case you're rusty on logs, just take e to that. Just e to that. It's just, and then you'll get back to the brain weight. These two are inverse functions, exponentiation and logs. I know a lot of you are not from, you took it, I'm sure you know it, but you're rusty, you haven't taken math for a while. So just play around on your calculator, and it will come back to you really easily. And I don't think you're going to have a problem with it. So please don't say, oh, logarithms, I can't even remember what they are. Don't worry about it, okay? So we're just going to because it will come back. So we're just going to exponentiate both sides and anti-log it. So we anti-log that. That's what we're doing to get the brain weight. And so the brain weight is just e to the 3.382. And now we get the brain weight, which is in grams. Okay? So what's the cat's residual here? The actual brain weight of the cat in the scatter plot is this. So this is the actual. What's the residual? That's our predicted. So the residual, the error, obviously, is equal to the actual minus the predicted, as usual, which is equal to what? 25.6 minus that. So the cat's a little bit below the line, but it was pretty close. And now let's do the human and see the human's residual. All right? So now let's just do the same thing for human, who is 62 kilograms, the one pictured in the plot. Okay? That's what I'm doing. I'm looking at the one in the plot. This was the cat in the plot. All right, so here we're going to do the same thing. And so let's just copy down the equation we're using again. So now it's the log of the brain weight equals 3 plus 0.32 times the log of 3. So this is what we're using. Whoops. Look what I did. I copied down the wrong. That's body weight times the log of the body weight, in which case, what is it here? It's going to be 62. So cross that out. It's 62. It's just right there's body weight. Okay. So now we're just going to calculate that, which is 4.32. Okay? Just plug that into your calculator, and it's 4.32. So now we're not interested in the log. We want the actual brain weight, so we'll just do the same thing we did before. So the brain weight is just e to the 4.32, okay, which is equal to 75.24 grams. And now the actual brain weight in the plot is much bigger than that. So the actual is this. So what's the residual? So the residual is 320 minus 75.24, and that's huge. And that's why we saw in the graph that the human was way above the regression line. We can just look at it again. Okay, so that's the residual. We're looking at these two residuals for the cat. You see? So it didn't do a good job. This is the huge residual. It did pretty well for the cat, slightly below the line. All right? Any questions so far? So now, what are we going to do? We're going to look at confidence intervals, but before we do, I just want to show you the basic transformation that happens when you anti-log something. So we've got a regression, a line in logs, right? So I want you to show you, these are our parameters, beta naught and beta 1, and I want to show you what happens when we do the transformation, right? So we've got this right here and this, and where they appear. So in general, so just because, why do we want to transform back? Well, it's way more intuitive to anti-log and go back to, most people don't think intuitively in terms of logs, so it's just helpful to think of it in going back to the regular units. So the idea is this, that these parameters that are the coefficients here turn into the exponents when we anti-log it. This is where they're going to appear as exponents. So you can see that with this right here. So if we have this, right? I'll just write it again just so you can see. So the log of the brain weight is equal to 3 plus 0.32 times the log of the body weight. And what happens when we anti-log it? Raise both two. So this becomes the brain weight, and this is e to all that. Okay, so now it's just the rules of exponents, and please remember, if the exponents are added, when you like 10 to the, this is all I'm doing, something like, all right, just to refresh your memory, 10 to the 1 plus 3, that's going to be equal to 10 to the 1 times 10 to the 3, right? 10 to the 4th is equal to 10 times 10 to the 3rd. So just don't be insulted, the ones of you who think, why is she doing this? People forget these things if they're not using them all the time, okay? So I just want to remind you. So here when we do this, it's e cubed times e to the what? To that. Now, I'm just going to, this part, that's multiplication. It's commutative. So I'm just going to switch the order and write it this way. The log of the body weight times 0.32. Okay? Why did I do that? Because this part right here is just body weight. We have log of body weight and we anti-log it, so we're back to body weight. So that's why we get e cubed times the body weight to the 0.32. And as I told you, these exponents right here, these coefficients right here, these become the exponents. That's all. So, now, what if we had been in base 10 instead of base? What if we had taken log? What if we were doing all this in base 10 instead of natural logs? Okay? What would we have gotten the same equation? If not, what would change? Well, only the intercept would change. The slope would stay the same. So really, and we don't pay much attention to the intercept, so we basically would have the same relationship. Holds up no matter what base you're in. Which would make sense. Why, I mean, all we would have to do, you don't have to know this, but the idea is all you'd have to do is divide both sides through by a constant. That's all you would have to do. Okay. So now let's go on. Boy, we're going to get out early, thank goodness, right? I've kept you so long most of the semester. We were rushing through it. Now it looks like, okay, we are only going to go through 43, right? And we just had an exam, so let's just finish this page and then we're going to go home. All right. So now what are we doing here? So we transform the variables, okay, to get the errors to be more normal, and that means that the standard deviation of the errors we use to compute confidence intervals has to be used. That's for the transformed variables. Okay? So how are we going to get confidence intervals? That's the question. So we're assuming I should write this. So this is what you do. You assume after you've checked everything, and we did assume the errors assumptions are met. And now we're ready to actually build confidence intervals around these point estimates. Okay. So the idea is, okay, so we're going to have to do it in 2 steps. This is the usual thing we always do. 68% critical value. We're going to use normal curves here because we're assuming things follow the normal curve. 95%, this is Z star, 1.96 really. So we're just going to do it very simply using our usual confidence intervals, right? So it's going to be our prediction, but it's the transform prediction because we are using these standard errors that come from, we're going to be using this right here, and that comes from the transform. That's the errors around our regression line, around the logs here. So we're going to do this, and then we're going to, so we'll get endpoints, and then we're going to anti-log those endpoints, all right? We can't use this on our predictions, right? We can't use it on what we predicted. Like here's our actual prediction here. We can't apply that to that. And so you'll see. All right. So we're just going to, so we first do confidence intervals for the log transformation. So, all right, so what did we get here? We used this equation, right? And we got that the log of the brain weight, let's just write this down from the previous page. So what did we get for our prediction here? We got this to be, we did it here. The log of the brain weight, the actual brain weight, it's right here. This was the log of the brain weight, right? We did this first. So this is what we're going to attach the error bars to this, when what we really want is this. So we're going to attach it to this, and then we're going to anti-log the endpoints to get a confidence interval around the brain weight, okay? So we're just building a confidence interval around our log equation. All right, so that's what we got, 3.382. So that's what we have. Then we did estimate the brain weight to be what? That. We'll put that in here, 29.43. But we want confidence intervals around this, but we can't do it directly. We have to do them here, get the endpoints, and then exponentiate those endpoints, and then they'll be around this one. All right. That's what I say here. Remember, this right here is for the log, not the brain weight. So we have to do this two-step process. All right? So first, what are we going to do? Okay. So first, a 95%, okay, just our usual way. 95% confidence interval is going to be our prediction, 3.382, plus or minus what? Can we just use 2 instead of 1.96? We're just going to use 2 times, we're using this. Those are our errors around the log prediction. So if we plus and minus one of those, we have a 68% confidence interval. 2 of those will be 95, so we want 2 of those, okay? So we can put the endpoints right in here. We can put the endpoints of the interval. If we added and subtracted 2, we'd get 3.82 plus 3.2, so that's 6.582. That's 3.382 plus 3.2. And then, of course, this one's going to be right here, is going to be 3.382 minus 3.2. So let's get those. And that's 0.182. Notice this is our usual confidence interval. Notice that our estimate is the midpoint of that, right? Our estimate, our prediction, 3.382 is right in the middle there, is the midpoint. It's not going to, why I'm saying this, so this is a symmetrical confidence interval. That's the way we always have been doing it, the confidence interval symmetrical. But now it's not going to be, because what we're going to do now, what do? Well, now we're going to take these and anti-log both of them. So for this one, we'll just say E, right, to the lower endpoint, to transform it from a log to a brain weight. So this is the confidence interval for the log. Now we're going to transform it to the brain weight. And look what we get. 1.2. Now we're going to do the same thing here. E to the 6.582. And this is going to be a really big number, 722. These are in grams. Now, we don't have we're building a confidence interval around this. So this is our estimate. But it's not the midpoint. It's much closer to the lower end, because when you raise x, look what we're doing, you're going to make this much bigger. So this is not the midpoint. So these are asymmetrical confidence intervals. The confidence interval is symmetric for the log of the brain weight, right? You add these two together, take their average, and you're going to get that. But you add these two together, the average of this is not that, but it is the geometric mean. So but it's asymmetrical for brain weight. Instead, it's not the arithmetic mean, it's the geometric mean. What do I mean by that? So if you want to check to see if these are right, you could say 29.43 is not the average of those two, far from it. It's much closer to this, but it is the square root of their products. So that's a good way to check. And you can probably see that just from, look what we did.